Today we're going to talk about buoyancy force, which is the upward directed force applied to an object by a fluid that it has been placed into. But beyond that, I wanted to take the time to look at the nature of compressible objects exposed to this buoyancy force. To do this, I've filled 3 balloons with varying amounts of rice screws and a little bit of air. The rice is mainly to hold the baseline volume, while the screws are to increase the density, and the air acts to decrease the density. This is also our compressible component. I'll place them in the bath one at a time to illustrate the densities. The first will be the least dense, and we'll see that it floats. The second is denser than water, and it will surely sink. But I wanted to have a third balloon as close as possible to the density of the water. And we'll see that while it does float, a much larger portion of it is submerged under the water than balloon 1. If we take a closer look, we can also see that a very small portion of its volume peaks above the surface of the water, telling us that it's not quite neutrally buoyant. Neutral buoyancy is when the object's weight is balanced by the buoyant force, which in this case would mean a net zero force. Which begs the question, what will happen when I push the nearly neutrally buoyant balloon to the bottom of the bath? Okay, interesting. It stays at the bottom. This could support our theory the force is balanced, and whatever height I place at the balloon at, it should stay, correct? If it's neutrally buoyant. Well, let's see what happens when I place it in the middle of the bath. Now would be a good time to pause if you would like to take a guess. Okay, so it floats to the surface. I'm going to try a few more times as is possible. It had a slight initial velocity when I released it, but hopefully you'll see with a few more attempts that it is in fact accelerating, and the net force is therefore not zero. Given that there are only 2 forces we can recognize here are the weight and the buoyancy force, we can expect that one is dominating the other, likely based off of depth. If the weight dominates, we should see the balloon sink, and if the buoyancy force dominates, we should see it rise. But what values are actually changing? In this formula, there are not many variables that can alter. As far as the weight, well, the mass is fixed, and the acceleration from gravity isn't going to change. The buoyancy force is based on density of the fluid, but fluids are considered incompressible, so I can't imagine that the density will change either. So how about volume? The volume of the fluid displaced is equal to the volume of the balloon, assuming it's fully submerged, and the volume of the balloon can change if compressed. That's what the air is for, after all, and this change will follow the ideal gas law. I hope you enjoyed the demo. I feel as though it takes a lot of concepts and links them together in a satisfying way for students. The example extends out to scuba divers who are frequently adjusting their buoyancy based on depth to minimize the effort of ascending and descending. In fact, you may already be familiar with the Cartesian diver exercise, which illustrates the same concept. I will argue, however, that this is more intuitive and highlights the pressure gradient we see in bodies of water. There are many immediate examples of problems you could have students do if they were simultaneously doing pre-calculus, like finding the gradient of water pressure with respect to depth, or even calculating the compressibility of air if one were inclined to set this up as a lab. Thanks for watching. I hope you find a chance to use these demos in the future.